This is the seventh in a series of resources that look at matrix algebra. We define and provide basic information about matrices. We consider the operations that allow us to manipulate matrices. We discover how to use the row operations to solve a system of equations using matrices. We consider various operations on pairs of matrices, including adding, subtracting, linear combinations, and multiplying. We learn how to find the inverse for a matrix. We discover the determinant for matrices and learn how determinants allow us to solve systems using Cramer's rule. When we considered inverses, we looked specifically at square matrices. That is, matrices that have the same number of rows and columns. Each square matrix has a numerical value attached to it, called the determinant. If the determinant is 0, then the matrix will have no inverse. The determinant also becomes very important in future topics in linear algebra. We will only consider finding the determinant and look at one specific application for the determinant in the next resource. So how exactly do we find a determinant? How we find a determinant depends on the dimensions of the matrix. First, let's consider the relatively simple 2 by 2 matrix. In general, these matrices equal A sub 1 and A sub 2, then B sub 1 and B sub 2. To find the determinant, which is sometimes shown as a set of absolute value brackets around a matrix, we subtract the product of the values along the main diagonal minus the products of the values on the off diagonal. In our general case, this means we have A sub 1 multiplied by B sub 2 minus A sub 2 multiplied by B sub 1. Let's see an example. Suppose we have matrix A equal to 7 and 4, then 5 and 3. We want to find the determinant of matrix A. To do so, we need to subtract the product of the main diagonal minus the off diagonal. We have 7 times 3 minus 4 times 5. This gives us the determinant of matrix A equal to 21 minus 20. So the determinant of matrix A is equal to 1. But how can we find the determinant of a larger matrix? Finding the determinant of a 3 by 3 matrix is much more involved than finding one for a 2 by 2 matrix. Any 3 by 3 matrix will look like A sub 1, A sub 2, and A sub 3, then B sub 1, B sub 2, and B sub 3, then C sub 1, C sub 2, and C sub 3. To find the determinant, we must introduce a new concept called the minor. This is the determinant of the portion of the matrix that remains if we cancel out a row and a column. When finding the determinant, we work across the top row. We multiply each entry in the top row multiplied by the minor for that position. The determinant of the entire matrix is then the sum of these products with alternating signs. So the determinant of matrix A is equal to A sub 1 multiplied by its minor minus A sub 2 multiplied by its minor plus A sub 3 multiplied by its minor. Let's look at an example. Suppose we have matrix A equal to 1, 2, and negative 1, then 3, 0, and 1, then 4, 2, and 1. We want to find the determinant of matrix A. To find this determinant, we work across the top row, finding minors. We have 1, the entry in the first position in the top row, multiplied by the determinant of 0 and 1, then 2 and 1, which is what remains when we cross off the top row and first column. We then subtract 2, the entry in the second position in the top row, multiplied by its minor. Crossing off the top row and the middle column, the minor will be the determinant of 3 and 1, then 4 and 1. We finish by adding -1, the element in the last position in the top row, multiplied by its minor. Eliminating the top row and the rightmost column, the minor is the determinant of 3 and 0, then 4 and 2. The determinant of matrix A will be 1 multiplied by the quantity 0 times 1 minus 1 times 2, minus 2 multiplied by the quantity 3 times 1 minus 1 times 4, minus 1 multiplied by the quantity 3 times 2 minus 0 times 4. Completing the calculations, we have the determinant of matrix A equal to -2 plus 2 minus 6, which equals -6. Finding the determinant of a 3 by 3 matrix was a lot of work. It is easy to forget certain aspects, like to alternate adding and subtracting. Luckily, there is an alternate method for finding the determinant of a 3 by 3 matrix. Suppose we have the same generic matrix, A equal to A sub 1, A sub 2, and A sub 3, then B sub 1, B sub 2, and B sub 3, then C sub 1, C sub 2, and C sub 3. To find the determinant, first we copy the first 2 columns to the right of the matrix. We will have A sub 1, A sub 2, A sub 3, A sub 1, and A sub 2, then B sub 1, B sub 2, B sub 3, B sub 1, and B sub 2, then C sub 1, C sub 2, and C sub 3, C sub 1, and C sub 2. Next, we find the product along each diagonal, both from the top down and from the bottom up. We then combine those products. If the diagonal was from the top down, we add the product. If the diagonal was from the bottom up, we subtract the product. Let's look at an example. Suppose we have matrix A equal to 2, -4, and 3, then 3, 1, and 2, then 1, 4, and -1. We want to use the shortcut to find the determinant of matrix A. First, we add on extra copies of the first 2 columns. We have 2, -4, 3, 2, and -4, then 3, 1, 2, 3, and 1, then 1, 4, -1, 1, and 4. Now we will find the products of the top-down diagonals. D sub 1, the first diagonal, is the product of 2, 1, and -1, which equals -2. D sub 2, the second diagonal, is the product of -4, 2, and 1, which is -8. D sub 3, the final top-down diagonal, is the product of 3, 3, and 4, which is 36. Next, we find the products of the bottom-up diagonals. U sub 1 is the product of 1, 1, and 3, which equals 3. U sub 2 is the product of 4, 2, and 2, which is 16. U sub 3 is the product of negative 1, 3, and negative 4, which is 12. Now we can find the determinant. We add all the top-down diagonal products and subtract all the bottom-up diagonal products. We have negative 2 plus negative 8 plus 36 minus 3 minus 16 minus 12. Combining, the determinant of matrix A is negative 5. But what exactly can we use this determinant for? As mentioned, the determinant has many uses in linear algebra. We will focus on one particular use, Cramer's rule. But what does Cramer's rule do for us? Stay tuned to the next resource in the series.